In our second video regarding planetary motion, we're going to take a look at what rotation is and how planetary rotation differs from planetary orbits. So another word that kind of means the same thing as rotation is the word to spin, meaning to move along itself like this, and in which case we're looking at the movement of the planet itself as opposed to looking at the movement of a planet around a larger object like a star, the way that we do with orbits. So in order to understand how planets spin, we need to talk about something called a rotational axis, which is simply a straight line that you can draw through the center of a planet, and the planet spins around this rotational axis here. Now, we can see that Earth's rotational axis is actually not completely straight. So this is a straight line that is 90 degrees from the horizontal, but we can see that Earth does not spin exactly like that. It's actually tilted at an angle of approximately 23.5 degrees like this, which causes the Earth to be slightly tilted, and we'll explain what the significance of this tilt is when we talk about how rotation determines day and night cycles. So if we draw the sun here in order to show its position compared to Earth, we can see that sunlight is hitting this side of the planet here, and therefore this side of the planet here that includes Europe and Africa as well as the Atlantic Ocean, this side is the day side of Earth. However, as Earth rotates along its axis like this, it's going to turn and therefore expose the Americas, North and South America, to the sun, meaning that they will be in their day cycle. So day and night cycles are simply decided on which side of the Earth faces the sun. So, for example, here in this position, Asia and Australia and all of the South Pacific Islands would be on the night side of Earth because no sun is able to reach them until the Earth rotates, exposing them to the sun and therefore bringing them to the day side. Now, even though the axis of rotation and Earth's rotation is quite interesting to study on its own, if we look at other planets, we can see very unusual features of their axis of rotation. So Venus's axial tilt is actually 177 degrees, meaning that it is almost 180 degrees. So what this means, if we start from the exact northern point, if we treat the axis as being a straight line through Venus vertically, its axial tilt means that the planet is tilted down like this, so that you can effectively think of Venus as being upside down compared to the Earth. Now, what this means, we can see that Earth rotates from left to right like this, but because Venus has basically been flipped on its head, that means that Venus rotates in a right to left direction, which is actually the opposite direction as every other planet. And Venus is the only planet like this because it's the only planet with such an extreme axial tilt. However, if we take a look at Uranus, it's an even more interesting case because we can see that Uranus's axis is tilted approximately 90 degrees so that the North Pole, if you will, of the planet is actually on its side here. And we can see from Uranus that this is the side where sunlight is hitting it, so this would be the day side. The difference between a planet like Uranus and a planet like Earth, however, is that this day side of Uranus always faces towards the sun, which means Uranus has one side of constant day, while the other side that always faces away from the sun is going to be a side in which we have constant night. And again, Uranus is the only planet in the solar system where this is true because it is the only planet that has such a specific axial tilt of being close to 90. Now, if we go back to Earth, Earth's axial tilt and how it rotates, especially when combined with its orbit, actually explains why Earth has 4 distinct seasons. So if we start, remember we learned the terms aphelion referring to when a planet is closest to the sun, and perihelion, the point in its orbit where a planet is farthest from the sun. The 2 points of Earth's aphelion and the 2 points of Earth's perihelions correspond to very specific times in Earth's calendar. So points at which the Earth is at perihelion, the farthest point from the sun, are what we call a solstice, while points where Earth is at the aphelion are what we call equinoxes. And we're going to explain what the significance of these is depending on what season we're in, which in turn depends on which side of the Earth is facing closest to the sun. Now, a surface level guess would expect, okay, winter at the perihelion makes sense because this is the point at which Earth is farthest from the sun, so logically we would expect this side of the Earth to be colder, but the problem is that really doesn't make a lot of sense because the opposite perihelion corresponds to summer. So what exactly is going on? Well, we can actually see, because of Earth's axial tilt, that if we draw lines from the sun to the Earth, we can see that sunlight does not hit every part of the Earth exactly equally. We can see, because of Earth's axial tilt, that the sunlight is hitting the northern hemisphere, which it is here, more than it is hitting the southern hemisphere, because the southern hemisphere is tilted away from the sun at this perihelion, while the northern hemisphere is tilted closer toward the sun. So if the northern hemisphere is tilted closer to the sun, more sunlight means the weather will be hotter, and therefore we would expect it to be summer in the north. And this corresponds to the summer solstice, which is actually June 21st in the northern hemisphere, because again, the north is tilted close towards the sun, but because the south is tilted in the opposite direction, we would expect that they would have the opposite season of winter while the north has summer. And if we go to the opposite side here, we can see that more sunlight is hitting the southern hemisphere. Again, remember that Earth rotates here, than the northern hemisphere. And we can clearly see, especially on the night side, that the north is tilted away from the closest point to the sun. So here, the southern hemisphere is actually closer to the sun, which means that the season in the south is going to be summer, which I can totally spell. Summer in the south, but again, as the north is tilted away from the sun because of Earth's axial tilt, this is why we have winter. Now, if we look at the two aphelion points, we can see that sunlight is basically hitting both hemispheres relatively equally. So therefore, as we rotate or as we orbit away from the perihelion here, we would expect autumn, which I can totally spell, autumn in the north, and simultaneously we would expect spring in the south as we transit between the two equinoxes. And then likewise, during the autumn equinox in the north, we would expect to find spring in the south, and vice versa. So this explains why Earth has seasons, which actually combines our knowledge of both rotation along a rotational axis, as well as combining it with the Earth's position depending on where the Earth is in orbit. The final feature that can be explained by rotation is rather interesting and concerns the moon. So, when most people think of the moon, they think of the moon looking like this, and regardless of what time of the year or what time of day that you can see the moon, we can only ever see one side of the moon, the side that looks like this. Now, why is this? Well, the answer would have to be that as the moon orbits around Earth, remember that the moon is also rotating itself. So the reason why we can only see one face of the moon, or one side of the moon, is that the moon rotates. Let me spell that correctly. The moon rotates on its rotational axis at exactly the same speed that it orbits the Earth. So again, as the moon orbits in its orbital path around Earth, the rate at which it rotates causes the same side of the moon to always face Earth, and that's why we refer to the side of the moon that we don't see as the dark side of the moon, because it never faces the direction of Earth. This phenomenon is what we call tidal locking, where one rotational object rotates at the same rate at which it orbits around a larger object in the solar system. And the moon is probably the best and well-known example of a tidally locked orbit. In the final video in our series regarding planetary motion, we're going to take a look at the significance of orbits and rotations of artificial constructs such as satellites and space stations.